Hello everyone, and welcome to the Linear Regression with Python lecture. Now that we've learned about the theory behind linear regression, let's go ahead and use scikit-learn to implement our own linear regression models. We'll start off by working with a housing dataset, trying to create a model to predict housing prices based off of existing features. Since linear regression is our first machine learning algorithm, we'll work with some artificially created datasets. Later on, we're going to progress to using real and messier datasets from Kaggle and other sources. But right now, we don't want to focus too much on cleaning our data. We'll focus on that aspect later on. Right now, we just want to get the basics of creating the model correct. Let's go ahead and jump to the notebook to get started. Alright, here I am at the Jupyter Notebook. As a quick reminder, you can find all the notebooks and all the data for this section of the course under Machine Learning Sections folder under the Linear Regression folder. We're going to be working with this usahousing.csv file, and the lecture notes are under Linear Regression with Python. This Linear Regression notebook is the one I just created and I'm working with now. I would also recommend that if you're working along with this lecture, you create your notebook in the same folder. Let's go ahead and get started. First thing we need to do is our imports. What's going to happen is we're going to say import pandas as pd, then we're going to say import numpy as np, and then we need to do our visualization libraries. We'll go ahead and say import matplotlib.pyplot as plt, and import seaborn as sns. And then in order to see these visualizations in the notebook, I need to specify matplotlib inline. Okay, let's go ahead and check out our data. I'm going to create a data frame called df and say pd read csv and call USA underscore housing. And then let's go ahead and check out the head of the data frame. In this data frame, we have a couple columns. We have every row representing a particular house at a certain address, which is the last column. And that house sold for a particular price. And then the other columns represent statistics for the city or area that the house was located in, such as the city's population, the average number of bedrooms for houses in that area, the number of rooms on average for other houses in that area, the average house age for houses in that area, and then people's average income for the houses in that area. So again, these first couple of rows that all start with average area are corresponding to the location or city of that house. And keep in mind that this data is artificially created, which is why we have such significant digits after the decimal point. You usually are not going to be able to have that much accuracy. Let's go ahead and explore this data just a little bit. What I would always recommend you do is check out the info method on your data frame, and that's going to inform you of the total number of columns and the total number of entries, as well as give you hints or statements on what type of objects are in the data frame. The other thing I would also recommend you do is to call the describe method off your data frame in order to get a quick account, describe, a quick account of some statistical information of your data frame, such as the mean, minimum, maximum, standard deviation, etc. of all the columns, at least the numerical ones. Notice here the address column is not available because that was a string value. And then another quick note, if you ever need to reference what the column names are, you can just say df.columns, and it'll return back a list of the column names. And notice here that there's spacing in between some of the words here. Let's go ahead and do some simple plots to check out the data. One very simple plot you can do if the data isn't very, very large is Seaborn's pair plot, and then you can just pass in the entire data frame. And this will automatically create not just histograms of all the columns, but also correlation scatter plots. And this is what that looks like. We can see the histograms, looks like everything's more or less normally distributed, except for the average number of bedrooms. And you'll notice that the average number of bedrooms is segmented into 2, 3, 4, 5, and 6, which kind of makes sense. There's some noise around there, but you can't have usually 2.5 bedrooms, which is why this sort of behavior shows up. Okay, let's go ahead and just check out a distribution of one of the columns. You'll probably usually want to check out the distribution of your target column, or what you're trying to predict. In this case, we're trying to predict the price of the house. So let's go ahead and check out the distribution of the price. Okay, it looks like the average price is falling somewhere around the 1 million mark, somewhere between 1 and 1.5 million, and everything looks to be normally distributed from there. That won't always be the case as far as pricing goes, or any other target variables. They may not be normally distributed, but this is a nice case since we're not really working with cleaning this data. And then something else you may want to do for a data set is to do a heat map of the correlation between each of the columns. So you can say df.corr to get the correlation matrix. And let me go ahead and just show you what that looks like. df.corr. This shows you the correlation between all the columns. And then you can plot that out as a heat map by passing that in through sns.heatmap. And here we can see you'll usually see a diagonal of full correlations, which makes sense because every column should be perfectly correlated with itself. And then you'll also see some information based off of other columns. Right now we get a lot of gray and low correlation amounts. And you can actually see this numerically by saying anot equals true. And this will pass in the actual numbers for the correlation. Okay, let's go ahead and shift our focus now to actually using scikit-learn and training a linear regression model. Okay, the first thing we need to do is split our data into an X array that contains the features to train on and a Y array with the target variable, in this case the price column, which is what we're trying to predict. We'll go ahead and toss out the address column because right now it only has text information that the linear regression model can't use. Later on throughout the course, we'll learn about natural language processing, which will allow us to work with text information. I'm going to go ahead and say df.columns to grab my column names, and then I will set x equal to df and then pass in a list of the column names. I can just go ahead and actually grab this from here and paste it in. And those are my features, and then y is going to be my target variable, what I'm trying to predict. In this case, that's just the price column. Now that we have our x and y data, our next step is to do a train test split on our data. We want to split our data into a training set for the model and a testing set in order to test the model once it's been trained. Let's go ahead and use scikit-learn to do this. Scikit-learn comes with a train test split function, and you can grab it by saying from sklearn.cross-validation, and you can just actually do tab to autocomplete this, and select cross_validation, import, and you'll want to do train test split. Now something I always like to do is whenever you're working with a new function, such as train test split, is to do shift tab in the Jupyter Notebook to read the documentation string for it. You can actually expand this by clicking this plus button and scrolling down. Basically what we're going to be doing is passing in our x and y data and then specifying the test size. You can scroll down and see a nice example here where you say xtrain xtest ytrain ytest is equal to train test split xy test size and then also a random state, which we can also add in. Let's go ahead and copy this line. I'm going to go ahead and copy it, and I'm just going to paste it here and put it all on one line. All right, let's go ahead and set our test size to 0.4 and set our random state to 101. Let me go ahead and explain what's going on here. This is essentially just using tuple unpacking to grab your training set and your testing set. And you're going to have your X train and your Y train, and then you're going to have your X test and your Y test. Then, in the train test split function, you pass in your X data, your Y data, and you can optionally also pass in your test size. And test size is just the percentage of your data set that you want to be allocated to the test size. In this case, we're going to go ahead and allocate 0.4 for 40%. A lot of times, it's also really common to do 30% or 0.3. Then this random underscore state equals 101. You can just pass in a number here that's optional if you want it or not, but this essentially ensures a specific set of random splits on your data, because this train test split is going to occur randomly. In order to make sure that your random split is the same as my random split, go ahead and specify random underscore state is equal to 101. That way, we get the same random splits. Otherwise, your results may not match up exactly like mine. They'll still be correct, you just won't have the exact same results. All right, let's go ahead and run this. Now that we have our training and testing data, we need to create and train the model. So the next step is to say from sklearn dot, and linear regression is found under the linear underscore model family. So we say linear, and you can use tab to kind of autocomplete this, import, and we want the linear regression model. Okay, once we've imported the linear regression model, we go ahead and instantiate an instance of the linear regression model. I'm going to go ahead and make a variable called lm equals, and then say linear regression and instantiate it. So I'm basically creating a linear regression object. And then I'm just going to say lm dot, and then click tab to check out all the available methods. So I have all these available methods on my model. What I want to do first is use fit in order to train or fit my model on my training data. And fit, if we look at Shift Tab, takes in an X and Y, and it goes ahead and fits the linear model. In this case, I only want to fit my model to my training data. So instead of just passing X and Y, what I'm going to do is say X train, Y train. And note that I get an output telling me that the linear regression model has been trained. Notice also that I don't set this equal to any other variable object. This is already taking effect onto the object itself. So I don't need to say lm equals lm.fit. You can just say lm.fit. Okay, now the next step is to evaluate our model by checking out its coefficients and then seeing how we can interpret them. Let's go ahead and print the intercepts. I can grab the intercept by calling my model lm and then saying intercept, and then at the very end an underscore. Or you can just use tab autocomplete to see this. The next thing we can check out are the coefficients. And the coefficients are going to relate to each feature in our data set. You can grab coefficients by saying lm.cof underscore, and this will return the coefficients for each feature. Let's go ahead and create a data frame based off these coefficients in order to kind of organize this a little better. So each of these coefficients relates to the columns in X, or X train. So you can go ahead and check that out. These are the same columns in X and X train. What I'm going to go ahead and do is create a data frame off of these. So I'm going to say PD data frame, pass in the coefficients as my data, pass in the columns as my index, and I'm going to go ahead and say columns is equal to, I'm just going to say coef. Let's go ahead and set this equal to CDF for coefficient data frame. And whoops, this needs an underscore. There we go. And then let's check the head of, actually let's check the whole CDF. Okay, so here I have a coefficient for each feature. And if you want the more mathematical reasoning behind these coefficients and how they work, make sure you do the reading. But I'm going to briefly explain how to interpret these coefficients. Basically what this means, if we take a look at this first one, if we hold all other features fixed, a 1 unit increase in average area income is associated with an increase of $21.52 in price. And then for the second one, we could also say something like a 1 unit increase in the average area house age is associated with an increase of $164,883. And you can do a similar analysis for each of these features and the coefficients. Now, you may be wondering, does this actually make any sense? Probably not, because this is artificially created data. But if you want to do a real data analysis, you can actually repeat this project on the Boston dataset that is the same housing sort of data, but it's actually real. It's from a 1970 study, and you can find it in scikit-learn. Let me go ahead and show you how you can go ahead and grab that Boston dataset. What you can do is you can call from sklearn.datasets, import load Boston. And there's a link in your notebook, load Boston, no parentheses. There's a link in your notebook for the documentation on this data frame. But basically what you do is you say Boston is equal to load Boston, and then you call it. You actually call that function load Boston. And then if you check out what Boston is, it's essentially a dictionary with a bunch of information on it. And you can check out the description of the data set by saying Boston, DSCR, and this will print out the Boston houses price data set. Now this is real housing data that you can go ahead and repeat our analysis once we're done with this lecture if you want to do a similar analysis for house price data on a real data set. Keep in mind this data is though quite old, and then if you want to grab the data itself, you can just say data, and you'll see here you have data, and then you can also grab the feature names, which are right here. It's essentially the columns of your data frame, and then you can also grab the target, and these are the target prices in thousands. All right, so that's just a quick aside in case you ever want to repeat this if you're not satisfied with this conclusion, which is really not realistic that as your house gets old, you would get an increase in price. If these coefficients were negative, then you would say for each increase in unit, you get a downsizing in price for the house. Okay, we'll go ahead and end our first part of our analysis here. In part 2, we'll discuss getting predictions from our model. But before we go to part 2, let's do a quick review of everything we just did. First, we had to actually grab the data using pandas and pd.readcsv. We did a little bit of exploratory data analysis, but since this is artificial data, we're not going to focus too much on that. Later on, we'll see a lot more in-depth exploratory data analysis. But then we went ahead and separated our data into X and Y, where X is the features and Y is what we're trying to predict. We said from sklearn.crossvalidation, import train test split. We went ahead and split our data, specifying a test size and also specifying a random state, so your results are the same as what's shown in this video. Then we said from sklearn.linearModel, import the actual model, linear regression. We created a linear regression object, basically an instantiation of a linear regression model. We fit that model to the training set, and then we explore the intercept and the coefficients. And you can check out the Jupyter Notebook for this lecture if you want a larger breakdown on how to interpret these coefficients. And basically we just formatted the coefficients into a nice data frame in order to read them. And then at the end, we showed you how you can access a real data set from scikit-learn itself, sklearn.datasets, import load Boston, in case you want to repeat this sort of analysis on a real data set. But we're not quite finished yet. In part 2, we'll discuss how to actually grab predictions from our model based off our test set. Thanks everyone, and I'll see you at the next lecture.